And welcome back to A&P1 and our look at the muscular system. This is the slide where we left off. I didn't want to scare you by putting up the next slide, so I thought I would soften the blow a little bit with this slide first. But now that I've built the anxiety of what is coming up next, let's go ahead and put that slide up. So I want to start our look at muscle contraction with the understanding that I like to teach this as a good novel. And any good novel has a beginning, has a middle, and has an end. And any good book that you read, you always read from the beginning, move to the middle, and then to the end. You never really start a book by jumping into the middle. You don't start a book at chapter 5, read to the end, and then go back and read the first 5 chapters. That's lunacy. You don't do that. But that's what I'm going to do for muscle physiology. I'm going to take our story, which has a beginning, a middle, and an end, and I'm going to start it in the middle. And we're going to work our way to the end, and then come back and look at the beginning. And there's a reason for that. I need you to trust the process. I need you to believe in the madness, and this will all make sense. I will piece this story together for you. But know that we're going to start this in the middle, work to the end, and then come back to the beginning. And so with that said, the beginning or the middle of our story begins with the sarcoplasmic reticulum, this modified endoplasmic reticulum whose purpose is to store and release calcium. And calcium is what is needed to begin this process of actually having the muscles contract. The beginning part of the story is the communication. It's setting up. It's getting ready. But once we've released this calcium, we know that we're going to have muscle contraction. So we're going to start the story with what in the world are these sarcoplasmic reticulum doing, and how are they regulated? Because they need to be regulated. They can't just simply release calcium into the sarcoplasm, because that's going to cause muscles to be twitching uncontrollably and spastically whenever. So we have to regulate that. So how do we regulate that? Well, before we go there, let's kind of back up and understand that the chief purpose of these guys is to... Oh, I thought I selected. The chief purpose of the sarcoplasmic reticulum is to store and release calcium. Right? That is what is happening. So the sarcoplasmic reticulum, after a muscle contracts, the sarcoplasmic reticulum is going to reabsorb any excess calcium that may be present within the sarcoplasm. And it's going to do that through a pump. And this pump is defined as an integral protein. And it's an integral protein. It is a pump that is going to remove calcium. It's going to absorb calcium from the sarcoplasm. Now, another name for this pump, if you remember back to naming pumps, another name for this pump would be a calcium, because this is what we are removing, and we're using ATP to operate the pump or the protein. Right, so ACE here always refers to a protein, ASE. ATP is defining how we are powering that pump. and the calcium is telling us what we are moving with the pump. And so another name for these calcium pumps are calcium ATP ACE. All right. And so once we've removed any excess calcium from the sarcoplasm, we store it in the ends of the sarcoplasmic reticulum that are called terminal cisterns. Right, so the terminal cisterns are located at the ends of the sarcoplasmic reticulum. Now, so on one end, we've got calcium ATPases of our sarcoplasmic reticulum. On the adjacent end, we have another protein, another integral protein, that is referred to as a voltage-gated calcium channel. Right. Now, these voltage-gated calcium channels open and close based on changes in voltage. They open and close based on changes in voltage. And so they are not ATPases. They do not necessarily require energy to open like our calcium pumps do, but instead they rely on a change in voltage. In other words, a change in the distribution of ions across a membrane. Let me say that again. Voltage-gated calcium channels, which are going to release calcium, function based off of a change in the distribution of ions across the membrane. Calcium ATPases remove calcium from the sarcoplasm. Voltage-gated calcium channels release calcium into the sarcoplasm. So pumps are removing and channels are releasing. And what causes the change in ion distribution that allows for these voltage-gated calcium channels to open is an action potential. Now, this is understanding an action potential is going to be rooted in understanding the beginning of the story. So, if you don't know what an action potential is yet, it's okay. All right, we're going to get there. And so again, that action potential causes a change in ion distribution, which opens the voltage-gated calcium channels, and it allows the calcium to move into the sarcoplasm. When the action potential has left, calcium ATPase is activated. Remember, this is a pump that is using ATP to do what? To bring back in, to reabsorb, or to suck up the remaining calcium from within the sarcoplasm. So that's kind of where we are with that part of the story. So let's go through and let's see if this animation is going to play. Great, the animation is going to play. So you've got this in your student slides. All right, this is a great animation that shows the steps that I kind of just went over. And so the bulk of what we're going to be looking at in this video is understanding what is happening right here and right now with this video. And again, I break this down into step by step. Step A, Step B, Step C, Step D, E, and F. So let's look at what's happening here. In this initial screen, right, let's just roll through here. So we're going to come back to E, then F. Right now, everything is neutral. Here's the sarcolemma, right, where the where the, hold on one second. I'm going to go back to that. I just want to come up to the laser pointer. Very good. All right, so let's come back here. All right. So right now, this is the sarcolemma. Hold on. All right. This is really acting wonky. All right. Right here, this is the T-tubule. All right. This is the sarcoplasmic reticulum. Right here. Right. This edge is what we would define as the terminal cistern. So this is the terminal cistern. Right. We see all the calcium is in there. Here's the sarcolemma. Here's the T-tubule. Right. These guys down here, this is the calcium ATPase. These guys up here are the voltage-gated calcium channels. Right. So sarcolemma, T-tubule, sarcoplasmic reticulum with the terminal cistern, calcium ATPase, and voltage-gated calcium channels. And so what's happening here is, in A, the action potential spreads down the sarcolemma into the T-tubule. That's what you're seeing here, which activates the voltage-gated calcium channels to release calcium into the sarcoplasm. And then, once the action potential has left, so let's look at this here. Action potential is now leaving. Calcium, or the voltage-gated calcium channels close after the action potential leaves, and the voltage-gated calcium channels open. Here we go. And they reabsorb the calcium back into the sarcoplasmic reticulum. All right, so if we look at this as a step-by-step, right, here's the video playing over here. Here's my step-by-step. In A, let's come over here. Right. And so over here in, oh, and I stopped the animation. That's what I was afraid of. So here is the, okay, that's not working for me right now. So here is the sarcoplasm. Here's the T-tubule. In step A, everything is closed. There is no action potential. Voltage-gated calcium channels are closed. Calcium ATPase is closed, and the calcium is stored within the terminal cisterns of the sarcoplasmic reticulum. In B, our action potential is spreads down the T-tubule, right? And when that action potential comes down into the T-tubule, it causes the voltage-gated calcium channels to open. We've changed the voltage. Why? Because an action potential is an electrical stimulus. And so it causes those voltage-gated calcium channels to open, which in picture D allows the calcium to be released from the terminal cisterns into the sarcoplasm. Now, there's a lot that happens between D and F that we're not going to cover yet. We will, but we're not going to cover it yet. So, D, action potential comes down, opens the voltage-gated calcium channels, causes calcium to be released into the sarcoplasm. And E, action potential leaves, which means that the voltage changes, which allows the voltage-gated calcium channels to close. No more calcium is released. We still have calcium that's left here in the sarcoplasm, and that's what you're seeing happening here in F. The calcium ATPase is then opened which absorbs the excess calcium back into the terminal cistern. Right? Back into the terminal cisterns. And this process then starts over. Once a new action potential comes down into the T-tubule, it will allow for the calcium to be released once again. All right, so let's kind of back that up here real quick. All right, I'm going to run through this from beginning to end, all right, and you should be able to hopefully explain it just as I have explained it here in a few minutes. And you can rewind this as many times as you want. So again, let's back up here and we'll kind of play this from the beginning. So in the beginning, all right, the voltage-gated calcium channels are closed. The calcium ATPase are closed. There is no action potential. An action potential is generated. It moves down the sarcolemma into the T-tubule, forcing the voltage-gated calcium channels to open, releasing calcium into the sarcoplasm from the terminal cisterns. The action potential moves on. When the action potential leaves, the voltage-gated calcium channels close. This then stimulates the opening of the calcium ATPase proteins to reabsorb excess calcium from the sarcoplasm back into the sarcoplasmic reticulum, and more specifically the terminal cisterns. That is what we just looked at here. Being able to say that and explain that and maybe even teach that to somebody else is really going to help you in learning the material. Muscle physiology is a very detailed step-by-step process. And it is very detailed. And you need to take the time to learn that. And so while you are doing what it is that you are doing, I suggest stand in the mirror, in front of the mirror, and just recite this until you have it down pat, just like I did. Record yourself saying it. Listen back to it. What are you missing? Figure out what you're missing, re-record it. Listen to it again. Play it back. What are you missing? Do you have it? Do you have all the details? Great. But this is going to take time. Now, you are fortunate that you can replay this and listen to me on loop. Go through that process. But you need to be able to take the time to learn this. Your exam is going to be very much heavily focused on a step-by-step understanding of how muscles contract. Now, what I want to finish up with on this PowerPoint, on this segment, is a little bit more about what is happening, what is going on after the calcium is released, but before the calcium is reabsorbed. So once the calcium is released into the sarcoplasm, until the calcium is reabsorbed back into the terminal cisterns. What's going on? And to understand that, we have to understand the structure and the organization of those myofibrils. So remember, you had your muscle, which was broken down into fascicles, which were broken down into myofibers, and those myofibers were broken down into myofibrils. Those myofibrils are made up of two types of myofilaments, thick and thin myofilaments. And structurally, these proteins, these linear proteins, so they are tertiary proteins, look very different, but work with one another to activate contraction of the muscle. So let's start with our thick myofilaments first. So here you are seeing a thick myofilament, right, that is running right across there, right across that length. And So here's your myofilament. Right? And notice coming off of the myofilament are these little speed bags, like speed punching bags coming off, or hockey sticks that are coming off of the actual thick myofilament. These extensions are what we call myosin. And myosin is a protein that is going to be active during the process of muscle contraction. Right? And so this is the thick myofilament. The protein, myosin, are these extensions. Right? And myosin has two main segments. It's got a myosin tail, which attaches to the thick myofilament, and it's got a myosin head. And some, by the way, sometimes that tail is referred to as, sometimes the myosin head is referred to as a sidearm. Right? And so this here would also be the sidearm, and this would be the tail. Right? The job or the role of the myosin sidearm, or the myosin head, is to bind with a protein on the thin myofilament that is called actin. But in order for actin to bind to myosin, ATP must be bound to the myosin head. Right? And so that is an important thing for you to keep in mind. Right? So when we are looking right here, ATP must be bound to the myosin head before actin will bind to myosin. That is an important step for us to keep in mind. Now, what is this actin thing that I keep referring to? Well, actin is a protein that is found on the thin myofilaments. Right, so you've got these thin myofilaments that are now in place. Thin myofilaments are made up of three proteins. They are made up of tropomyosin, they are made up of troponin, and they are made up of actin. Right? Tropomyosin is this Twizzler or spaghetti looking structure that you see right there. Right? That is tropomyosin. Tropomyosin is responsible for covering the binding sites on actin. So actin has these binding sites. That's what you're seeing right here. And these actin binding sites is what will bind with myosin on the thick myofilaments. So if those sites are covered, actin and myosin can't bind. What covers those binding sites is tropomyosin. So tropomyosin is responsible for covering the binding sites on actin, which prevents actin from binding to myosin. Troponin, which is our second protein here. Troponin are these little yellow circular proteins that actually wrap around tropomyosin. I kind of like to, I use the analogy of tropomyosin, think of them being like the Twizzler strings, all right? And then remember the old candy bracelets that you used to be able to like put on your wrist or around your neck and you could sit there and chew the candy off of them? Yeah. Well, those candy bracelets are troponin. Right? And so troponin kind of wraps around tropomyosin just like a candy bracelet would wrap around like a Twizzler or something like that. or your wrist. The job of the job of troponin is to bind to calcium. Calcium binds to troponin. Where's that calcium coming from? It's the calcium that was released from the sarcoplasmic reticulum. And when calcium binds to troponin, it forces tropomyosin to spin. And when tropomyosin spins, it uncovers the myosin binding sites on actin. So let me say that again. Calcium released from the sarcoplasmic reticulum binds to troponin, which then forces tropomyosin to spin, which uncovers the myosin binding sites on actin and grants permission for actin to bind to myosin. And that happens assuming ATP is also bound to myosin. Remember, both molecules needs permission from their parents to play with one another. Myosin needs permission from its parents, aka ATP. Actin needs permission from its parents, that being calcium bound to troponin. If calcium isn't present, actin can't play with myosin. If ATP is not bound to myosin, myosin cannot play with actin. In other words, no contraction will occur. Right? No contraction will occur. And so I want to kind of stop there and give you time to digest this material. I know it is a lot. And so I do want to kind of honor that and give you a few minutes to digest those steps that we've just talked about. And then we're going to come back here and look at some more organizational type stuff. So with that said, part 2 is done, and I will see you on the flip side.